Hi, my name is Taylor Alexky. I'm a physics teacher's assistant at Santa Rosa Junior College. I am also part of the Teaching Fellow program for the 2019 and 2020 school year. Today, I'm going to be doing an introduction to drag force. Drag force is a resistant force an object experiences as it moves through a medium. One medium we'll look at in particular is air, but objects experience drag force as they move through liquids and other types of gases. Drag force depends on mass, shape, and speed of the object, and the type of medium that the object moves through. The equation that we use to describe drag force is equal to 1/2 times the drag coefficient. This is dependent on the object. Rho, which is the density of the fluid. A, the cross-sectional area facing the fluid. And V, the instantaneous velocity of the object raised to some power. I have provided a table of various shapes and their corresponding drag coefficients. Objects that are more aerodynamically shaped have a smaller drag coefficient. Objects that are less aerodynamically shaped have a larger drag coefficient. If we look at the streamlined body, which has a drag coefficient of 0.04, we can see that it's a very aerodynamic shape, and it's actually the shape that most planes are modeled after. And that's to minimize air drag, the drag force experienced when traveling through air. Another important relationship is that drag force is proportional to some power of velocity. We find that this power depends on the type of fluid, and for lab, we want to determine what relationship is best for an object traveling through air. Is air drag proportional to velocity or to velocity squared? I provided free body diagrams of a free-falling object. In free body diagram A, we see that the object is released from rest and only has weight acting on it. As the velocity increases in B, C, and D, we see that the drag force increases as the velocity increases, while the weight stays constant. Another important point I want to make is that the drag force opposes the gravitational force. And because drag force increases with velocity, it's different than other resistive forces that we've studied previously. Like if we contrast this with the frictional force depended on the coefficient of friction and did not change based on velocity. But drag force does. It increases as velocity increases. I want to show a demo of why shape matters. We're going to watch a balled up piece of paper fall next to a flat sheet of paper, and we want to see how shape can impact the amount of drag force experienced by an object.
Which one is going to hit the floor first? A or B? Make a prediction. And now let's see. 3, 2, 1. Was your prediction right?
Okay, so we see that in this demo, the balled up sheet of paper fell faster. It was able to cut through the air quicker than the large sheet of paper. So the shape meant that it experienced less drag force. We also want to look at how a fluid that an object is moving through can impact the amount of drag experienced. We're going to watch weight bearings fall through 3 different types of fluids. The fluid to the far left is propanol. It has a very low density. Propanediol is the fluid in the middle. It has a density somewhere in the middle. And glycerol has the highest density. And it's a very viscous fluid. Viscosity refers to the thickness of a fluid. It has a consistency similar to honey. So we're going to see how the density will impact the amount of drag force experienced by the weight bearings.
Okay, 1, 2, 3, drop. Okay, so the propanol is all the way down, propanediol following quickly, and the glycerol having 3 hydrogen bonding sites takes the longest.
Okay, so we saw that the glycerol took the longest. The higher the density, the more drag force was experienced by the object. So here's another diagram of the forces acting on an object as it falls through a gas or a fluid. So weight, if it's dropped from rest, weight is the only thing acting on it. As the velocity of the object increases, the drag force will increase accordingly. Eventually, the drag force will balance the weight. At that point, the object will no longer accelerate and it will continue to fall at a constant velocity. And this constant velocity has a special name, terminal velocity. Again, when the drag force balances the weight, the object stops accelerating and falls with a constant velocity called terminal velocity. So in this diagram, when the drag force balances the weight, the net force acting on the object is 0. So as velocity increases, the drag force increases, which decreases the net force. I provided a picture of a parachuter starting from rest. As he falls, the air drag increases eventually to balance his weight. And here the weight is balanced and we can see that acceleration is 0. So I provided a velocity versus time graph of an object in free fall. At point A, we see that it starts from rest, velocity is 0. As the graph approaches point B, we see that the object's velocity is increasing until it reaches point C, which is its max velocity, its terminal velocity, and at point C, the object is no longer accelerating. All right, thank you so much for listening.